Good evening, good morning, and good afternoon, everyone. Welcome to the Park course series, Fundamentals of China Knowledge Map, from classic to AI-based methods. My name is Junting from Southeastern University. Today, I'm very happy to chair today's session. And we are very honored for having Professor Junting Chen from the Chinese University of Hong Kong, Shenzhen, to give us a talk on blind utilization of CKM for CSI tracking. First, let me give a very brief introduction for Professor Chen. Professor Junting Chen is an assistant professor at the Chinese University of Hong Kong, Shenzhen. He is also with the Shenzhen Future Network of Intelligence Institute. Professor Chen received the PhD degree from the Hong Kong University of Science and Technology, and he received the Bachelor of Science degree from Nanjing University. His research interest includes the signal processing, optimization, and machine learning for wireless communications and localization. Also CKM, radio map construction and application, low altitude air-to-ground integrated communications. Professor Chen is an editor of IEEE transactions on wireless communications, and he also received the Charles Carr Best Paper Award, WOCC 2022. He is also recognized as top 2% scientist in 2025. Professor Chen is a workshop co-chair for CKM in IEEE GlobalCon 2025 and IEEE ICC, CIC, ICC 2024 and 2025. So without any further ado, let's welcome Professor Chen. Prof. Chen, you may share your screen.
All right, thank you for the very nice introduction. So let me try to share my screen. So is it working? Do you see my screen in full screen mode?
Oh, yes, perfect.
Okay, good. Okay, so hello everyone. So welcome to the CKM mini course, lecture 3.3. So this will be about blind utilization of CKM for CSI tracking. So you may have already attended the previous lecture where Professor Zheng and Professor Xu talk about CKM utilization for predictive communications and non-line of sight radar sensing. Now, in today's lecture, we'll focus on a slightly narrower topic where we discuss the issue where we do not have location information for free, and then how, and in this scenario, how do we utilize CKM to assist for the CSI tracking? Now, for those who are working on CSI estimation and CSI tracking, you may already know that this is a sophisticated problem. So we need to discuss it case by case or scenario by scenario. So today we'll focus on a very specific scenario for CSI estimation and tracking in FDD massive MIMO systems. Now for FDD, it actually refers to the scenario where we use the frequency division duplexing for uplink and downlink. So that means we use two frequency bands, which are typically far apart for uplink transmission and downlink transmission individually. Now with that, we usually need to use a different approach for channel estimation. For downlink channel estimation, we probably need the base station to send out some beam-formed pilots to the user, and then the user needs to estimate the channel and then feedback the channel state information to the base station. So this is the typical channel estimation mechanism in the FDD system. Now, in particular, we focus on the case of a massive MIMO scenario where a base station has NT antennas, where NT is typically large, say 10 to maybe 200 or maybe even a few more hundreds. And for the sake of simplicity, we simply assume that the user have a single antenna. So the scenario where the user have multiple antennas, will share the same methodology we discussed today, although the scenario will be more complicated. Now, it is known that acquiring the downlink CSI, for the downlink transmission is difficult because we have a very high degree of freedom to estimate the antenna status for each of the antenna. This is because when we have many antennas, the base station have the capability to form a very narrow beam towards the user. And when the base station does not know where the user is, they probably need to search over the entire space. And search dimension would roughly scale with the number of antennas. So say we have antennas, then we have 100 antennas, then the base station probably need to use 100 channel use in terms of the time frequency resource plots in order to know about the full antenna states, right? And this has to be done within a very short time frame, typically at the scale of 100 milliseconds. And this is called a channel coherent block. So this is because the channel is time varying as we are moving along the city, the channel is changing. And typically, we can roughly assume that right within 100 milliseconds, the channel remains roughly the same. So we only have 100 milliseconds to estimate the channel status. And if we go beyond that time frame, the channel probably change. So this makes the problem quite challenging in the sense that we need to estimate the full CSI within a very short time frame. And typically, we have some method. For example, the most typical method is the hierarchical beam sweeping, which has been deployed in most current systems. Say the base station first use wide beam to roughly localize the user. For example, I use a wide beam to scan the area. After scanning, I will know the user is roughly to the east of the base station. Now, the reason that the base station can use a coarse wide beam because it can sweep the entire area using just a very few number of wide beams. And then once we know the rough direction of the user, then the base station can form narrower and narrower beams and eventually pinpoint the exact location, the exact direction of the user, so that it can form a narrow beam to deliver a message to the user to enjoy a very high beamforming gain. And also, we have some alternatives, say compressed sensing, under the assumption that when we have many antennas, the MIMO channel could be roughly sparse, meaning that there are just a few number of dominant propagation paths between the base station and the user. Say if I just have 10 dominant paths, then probably I can just use 10 channel use to sense the channel, and then we have some compressed sensing algorithm to estimate the full CSI based on these few observations. And then now in most scenarios, the user can be moving, right? So the trajectory of the user is spatially correlated, and then correspondingly, the channel of the user is also temporally correlated. So that means although from the first 100 milliseconds to the next 100 milliseconds, the channel is likely to change, but it does not completely change. So that means I can use the historical information of my channel. I can use the past channel information to roughly predict the current channel state information. So in that sense, I don't need to use 100 channel use in every time slot to estimate the full CSI. So I can use some filtering approach, in particular common filtering approach, to keep track of my full CSI. So the focus of this talk is to investigate how channel knowledge map may help to keep track with the CSI. So we are not trying to build these existing methods. What we are trying to do is that on top of the existing approach, if in addition we introduce CKM, can we do better than existing approach? Now, to recap the basic concept, now CKM, as we have mentioned in the previous lectures, is a mapping from the transmit receive location Z to the channel knowledge, where the knowledge can include signal strength, delay, angle, etc. And then this knowledge is, of course, environment dependent. Now, so to use the CKM to assist for the channel tracking, we can think of this pipeline. So the first row illustrates the conventional pipeline for channel tracking, where so this is the channel to be estimated, and the system could adopt some probing strategy. For example, it send out some beamform pilots to acquire some pilot observation at the user, and then the user can run some channel estimation or tracking algorithm to estimate the channel. So if we have a CKM, say if we know the position ZT, or we may not know the exact position CT, but we may know some location feature of the current location, right? And then we can check the CKM, and then to find out any like prior information of the channel. And with some prior information, we may do better in estimation. So in this sense, CKM can at least help in two directions. One is CSI reconstruction, right, from the geolocation information, if we know that. And then it can also help to provide some adaptive probing guidance to tell the system where to search, in which direction should we search for the user, how can we like probe the user or beamform the pilot signals. Now, what we are interested in this lecture is that what if the location information does not come for free? What if we do not have the exact location CT, or maybe the CT, the location CT is not good enough for a CKM assistance? Now, this happens when we do not have access to a GBS, or maybe the GBS data is not updated enough. More specifically, we want to ask a question, can we jointly recover the CSI and the position from the limited pilots? Right. So the first attempt would be a process like this. Right. We probably use CKM to recover the location, right, based on some sparse observation of the user. Right. It can be based on some sparse pilots, or some pilot-like information. Now, suppose that we can recover the position P, and then we can use the position P as an index to check the CKM, and then to recover the full CSI. Right. So why does it work? Because the location has just 2 degrees of freedom. Right. We can only move in the 2D space, or even or 3D. Right, but we can make some observation of the channel. The channel has a very high dimension. Now, if we can make some observation, for example, 3 pilot sequence, then in principle, it is possible to already pinpoint where the location is. So the assumption behind is that there could be a one-to-one correspondence between some sparse CSI feature to the position. Right, where the position has just 2 degrees of freedom, and then the CSI feature can have much higher degrees of freedom. Now, this this table illustrates the fundamental idea. So we have a CKM that record every location, the location pair, the location and the CSI pair, where the CSI can consist of AOA, delay, or resist signal strength, etc. Now, suppose that we observe some partial information, for example, delay and resistance strength, and this may already be sufficient to pinpoint where the location is, right? Where the user is, right? Because the delay information can have a high dimension, and then the resistance strength can also have a high dimension. So when we have a sufficient observation, although it is only partial, we can pinpoint where the location, where the user location is, and then based on the user location, we can check this CKM table to acquire the full information of the channel, including the AOA, AOD signature, and then based on this information, we can recover the full CSI. Right. So this is the philosophy, and I'm trying to argue that it is possible to do so with CKM. We can use a small price. Pay a small price in terms of a very sparse channel observation to recover a full CSI. Now, however, this is actually more or less identical to the principle of compressed sensing, right? Because the end-to-end process is in principle to recover the full CSI based on some sparse observation, right? So this is what exactly the compressed sensing is doing. If our ultimate goal is to recover the full CSI, right? What compressed sensing does is that it tries to minimize the L1 norm of the some sparsity, some sparse representation. Try to recover some sparse representation of the channel, such that the observation agreed, such that the recovered channel agree with the observation, right? And then in order to solve the compressed sensing problem, we probably need to run some iteration, etc. Now, of course, the radial map approach goes beyond compressed sensing, right? In two sense, right? First, it may not need to do. It may not need to solve an iterative. May not need to solve a compressed sensing problem using iteration. Right. And the second one is that CKM can make nonlinear observation, right, related to CSI, whereas for compressed sensing, it can only make linear observation, right? According to this formula, right? For compressed sensing, we have an observation matrix to be multiplied with sparse representation of the channel. So for compressed sensing, it always need to use. It most likely need to use a linear observation model. However, for CKM, it does not have this constraint. So CKM is much richer concept than compressed sensing, although the end-to-end principle is the same, to try to recover the full CSI from sparse observations. So our problem is essentially a compressed sensing problem, but under a more general requirement, under nonlinear observation. And then we are interested in the case where we can use how we may use CKM as a prior to improve the observation performance. So the key question here is essentially, can we do better than classical compressed sensing in terms of under very few pilots, say M, the number of observation can be much smaller than the sparsity of the channel, right? So this condition is the requirement of compressed sensing. For compressed sensing, we need the number of observation to be to be at least larger than the sparsity of the channel. So with CKM, we may investigate whether you can break this constraint. And then can we do the recovery without the sparsity assumption? And can we do recovery algorithm without iterations? So a general framework can be the following. We have the conventional pipeline for channel estimation. And then we imagine CKM as a side auxiliary memory module, So it is a module that tries to apply information that assists for channel estimation, also provides some guidance for probing strategy to find where the channel, where the user is. And then eventually, we prefer this architecture because it may have the benefit that it can be served as a plug-and-play database or memory. So that means we can train or develop a system for maybe Shenzhen, and then apply this system to Beijing or London, just by replacing the CKM module. So the input is some sparse CSI observation or some sequential CSI feature if we are allowed to exploit the temporal correlation of the data. And then the output is the CSI statistics as well as the position estimate. And the principle we want to explore is that we'll try to discover the geolocation information from the massive amount of CSI data. So this is what we call self-localizing, right? The input is the CSI observation, and then by accumulating a large amount of input, we somehow self-localize all this data, and then figure out where we are, and then by utilizing the historical data, we can recover the full CSI or the full CSI statistics, and then to assist for CSI tracking. All right, so this is the general framework we want to study in this lecture. So so this is the outline. So we'll revisit the Bayesian framework for joint CSI and position recovery. So we have already roughly talked about this in lecture 2.4, where we studied blind CKM construction. And now we will see that when we talk about more specific problem for CSI tracking, we need a more sophisticated model, but the framework remains the same. And we introduce two tools. One is a model-based tools, where we develop a switching common filtering method. And the second tool is utilize deep learning, where we'll talk about recurrent neural network with CKM embedding. And finally, we briefly mentioned how do we do CSI probing and integrate everything together. Now, we need to first think of a channel model, right? Because we talk about CKM, we talk about memorize the CSI, then we need to first figure out what do we memorize and what cannot be memorized, right? Because the channel itself is random, it's time varying and random, right? So we try to understand the channel as a composition of two components. One is the channel that is due to static scatters. Now, for example, we have a very large building here, we have a bridge, etc. And this infrastructure can stay for years. And this occupies the large portion, a large part of the environment. So we consider that the major part of the channel comes from the scattering, from static scatters. And then we also have moving scatters, and we also contribute the second part of the channel. And then so this H epsilon capture the randomness due to moving scatters and also small scale fading. And so what to memorize? Instead of memorize the channel realization that is caused by the static scatters, it's better to memorize the subspace of this component, right? The reason is that this component, although it comes from static scatters, is also random, right? So this can be seen from this formula, where if we use a multipath a model, then the static component comes from this multipath, where the path gains AL can be random, right? Due to the small scale fading, right? Due to the fact that we move a little bit, then the channel, the phase will substantially change. And this is also due to some practical issue. For example, the antenna pattern may not be a perfect sphere, and then the way you hold your phone or the gesture of the phone may affect the antenna pattern and affect how the antenna responds to different paths. So this component is random. However, this component, so this is the steering vector for the propagation path. And this is strongly location dependent, right? Because this part essentially tell us the angle of arrival from the base station to the static scatter. And since the static scatter remains unchanged for a sufficient long time, then this is likely unchanged. Now, with this, we can understand that the subspace is more or less static, right? And then the random component is something quite random, and we don't hope that we can memorize this part. So with this, we propose to form a CKM model as a mapping from each position X to the statistics of the MIMO channel. And in particular, we try to use the covariance matrix of the MIMO channel to represent the feature of the feature at position X, right? In particular, the covariance channel will capture the randomness of both the static component as well as the random component. So we can imagine that for a static component, although it is random, but then it most likely points to direction east, right, to the east direction. But then for the random component, the component that is due to the moving scatters, it is probably location dependent, but it is so random that it behaves like spreading the energy towards all the directions. And then to simplify the for the sake of the complexity, right, we focus on a discretized scenario where we discretize the area of interest into some grid cells, and then we map each cell to a channel distribution, or more specifically, to the covariance matrix of associated with the particular cell. And so this is our radial map model: a cell from a discrete set to a covariance matrix. So this can this is an application example for this radial map model. Now, say we construct a few beams, like beamforming vectors, like Wi, where I from 1 to 10, for example. Each beam can correspond to a signal steering direction, right? And then if we compute the quadratic form between this beam and the covariance matrix, we get the MIMO beam map, right? So this is one application of such CKM model. Now, in addition of the CKM model, we also try to exploit the temporal correlation of the channel, right? This is because if we move a little bit in the geometric space, then the channel can only change a little bit, right, due to the strong correlation of the environment. Now, one common model to describe such temporal correlation is the so-called first-order AR model. Now, of course, we can also do high-model AR model. So for the sake of simplicity, I just use a first order. So the model is like this. So HT at the current time, the channel at current time equals to gamma times HT minus 1, the channel at the previous time slot, plus some perturbation. Now, without CKM, we don't have enough information to describe the perturbation. So in the literature, in a very classical AR model, people usually use IID vector to model the disturbance, or UT. Now, we have CKM, so we can do better. If we know where the user is, Then we know the covariance matrix of the channel, and we know that this channel properly have a distribution with covariance matrix being CXT. Then we can model the disturbance UT that follows the Gaussian distribution with covariance matrix CXT, where ST is the position. Right. So with this model, we can achieve the property that the statistics of the CSI variation strongly depends on the location x of t. So this is the CSI evolution model. And then we are interested in, as we mentioned before, we are interested in the case where we have just a very limited amount of measurement. So this is our measurement model. So we have the channel, full dimension, and then we have the so-called observation matrix, A of t, where each row of the observation matrix A of t is a beam-forming vector. Right? So Y of t is simply a noisy observation of the beam-formed pilot, where we simply assume that we are transmitting a pilot symbol s equal to 1. So essentially, this is, so there's a s equal to 1 here. So the goal, just to summarize, based on the model here, the goal is to develop a CSI tracking methodology under a very small m, where m is typically smaller than the channel sparsity, right? Whereas compressed sensing may not work. And then we also try to has the capability of CSI tracking under non-Lapsine scenario, right? So this is known to be difficult, where a common filter may not work. We will explain that later. And then we also talk about how to construct the covariance matrix C of xt, right, from a massive amount of yt, but then the yt is very sparse. Now, with that, we need to specify the model with more details. In lecture 2.4, you probably already know that this is essentially formulating and solving a hidden Markov model problem, where what we need to do is that we need to formulate a number of, say, observation model, mobility model, etc. Now, based on our construction, we can formulate the measurement model. So what we have is, given the location x of t, given the CKM, which provide the covariance matrix C of xt, and then given the observation matrix AT, we can actually formulate the probability, the conditional probability of the observation y of t, right? We'll see a detailed expression later on in the next slide. And then we also need a mobility model, right? It can be a parametric model if we use a model-based approach, or it can be a deep learning model if we follow a data-driven approach. If we have collected all the observation data, and then we lump all the location variable together, then using Bain's rule, we can formulate the joint probability between all the observations and all the footprint of the trajectory, right? And then we can formulate a maximum log likelihood problem to maximize this joint probability over the entire trajectory, the footprint of the user, the parameters of the propagation model, the parameter of the mobility model, right? So this is essentially the framework, the idea of the joint CSI and position recovery problem. Now, in the previous lecture, we have already seen how to solve this problem, right? Using a model-based approach, where in the previous lecture, we formulate the measurement model using a parametric model. Now, in this lecture, we'll also describe how to solve this problem using a data-driven approach, where we don't have some specific parameter for theta t, right? But we have covariance matrix, right, from CKM. And we also provide an alternative strategy to develop a deep learning driven approach to solve this problem where we don't have a parametric form for the mobility model. And we use a deep learning model to try to learn the mobility pattern hidden from the data. Now, to specify the observation model, right, we call that we have already modeled the channel as strongly as some random vector that has a statistics strongly dependent on the location, right? So given the location xt, we know the covariance matrix of the channel, so that we know that the channel distribution. And we also have the observation model. Then using Bayes' rule, then we can easily write down the probability distribution function observation. So this can be given in closed form. And then we can formulate a John likelihood problem, right? So with this, and then with the mobility model, then we can find a John probability between all the CSI observations, or the channel h of t, and then the in-time trajectory, right? Given all the observation matrix for every time t, as well as the CKM, right? In terms of the covariance matrix for each possible location. And the key to solve this problem is that we got to restrain our variable into a discrete set x, right? Otherwise, it's very difficult or maybe unable to solve. So the challenge is how to solve it recursively, right? For the sake of complexity, right? Because we are talking about a CSI tracking problem, right? So it has to be relies on a filtering type of a solution. Otherwise, it is not complexity friendly. So here is how common filtering comes into play. Now, suppose that we don't have a CKM, suppose that we are working in a line of sight scenario, then people can easily think of, right, maybe common filter is a good methodology. Or more generally, common filter is a tool to solve a general HNN problem, right? If all the observation and state transition models are linear with independent Gaussian noise. Now, of course, this is not the case in our problem of interest, but then it is very helpful to revisit the classical approach of common filtering. So for common filtering, it is just a set of a pipeline to run these updates sequentially, right? So given the observation up to time t-1, right, the best estimate of the channel at time t, given the estimate of the channel at time t-1, is given by this product, right, with parameter gamma, right? So this is due to our channel model, right? In our channel model, we imagine that the channel behaves like this. We have a gamma to describe the temporal correlation of the channel. And then we'll also update a so-called covariance matrix of the channel estimation error. So we'll come to that point later. But in a nutshell, so this is a matrix that characterizes how good our current estimation is based on the observation up to t-1. And then based on the observation t-1, the covariance matrix will be the covariance matrix at time t-1 plus some disturbance, right? So this is what makes the CKM assistant problem different from the conventional common filtering problem, right? In the conventional common filtering problem, we need to compute the variance or covariance of the perturbation. But then in the past, since we don't have a CKM, so we can only use identity matrix to approximate the distribution or the statistics of the perturbation. However, with CKM, we know that the perturbation has to be location dependent. So we have a better computation or better information of the location-dependent perturbation. And with that, we can have a better information or more accurate calculation of the error correlation matrix. And this is how CKM may enhance the capability from a conventional common filtering. Now, the remaining step is very classical. We also need to update the so-called gain matrix for the common filter, which depends on the error correlation matrix as well as the observation matrix. And then we'll update the channel estimate at time t, right, based on the path estimate as well as the gain matrix. And then we also update, and then based on this new update, we'll also update the correlation matrix of the error. So this is the classical approach of common filtering, where we would simply use the identity matrix to approximate the perturbations. So this explains why classical common filtering may not work in a general scenario where we have possibly line of sight and then line of sight, right? Because it does not have sufficient information to compute the location-dependent statistics without the CKM. So in order to do that, we need to do some additional approach operation to track the position, and then based on the position to recover the covariance matrix so that we are able to compute the statistics. So let's look at how to implement the whole structure. So again, the whole thing is we have the full CSI, right? And then we have a sparse observation. And based on the sparse observation, we run common filter light tracking algorithm to obtain a channel estimate. And this is the conventional common filtering. It is known to work well under a fixed domain. For example, in line of sight like tracking, right? Using common filter or extended common filter. Now, what we are going to do is that we are going to introduce some location-dependent module and a CKM, right, a database, so to assist of the tracking. And the motivation of that is to assist for domain switching. Switching from line of sight to line of sight, or switching from one propagation pattern to other propagation pattern. So let's see what it means. We need to track the distribution of the mobile position, right? For at time t, right? We probably already have the position estimate at pt minus 1, and then we also need a mobility prior, which gives the probability of pt given the probability at the position pt minus 1, right? With that, we can maintain a distribution of the position at time t. Now, with that, we can update the formula to compute the covariance matrix of the prediction error. And more specifically, the prediction error is modeled as the true ht, right, minus the estimate of ht given the observation up to time t minus 1, right, given the past observation, right, from the very beginning up to t minus 1. And the covariance matrix is simply defined as the covariance of the this vector, right, like this. Now, through some derivation, we will know that this covariance, the covariance matrix here equals to the covariance matrix at position pt, right, average by the distribution of the position pt, where pi t, pt again is the distribution of the position at time t, right, based on the observation up to t minus 1. Now with this, we have an estimate of the channel covariance matrix based on all the information that we have accumulated from the very beginning up to time t minus 1. Now with that, we have a better estimate or better or more accurate computation of this covariance matrix. And then we can also, based on this, we can also update the position estimate at time t, right, based on the transition probability, the probability of ht condition on ht minus 1, and times the probability, right, transition probability from the mobility model. So this is a summary of the key step of the switching common filter method for joint CSI and position tracking. Now, for the blue part, it is just the conventional common filtering step. And for the green part is the additional steps or some updated step, modified step introduced by switching common filtering. In particular, we got to maintain a distribution of the position, and we also need to update the position of the user. And then with the distribution of the position, we can maintain an update of the covariance matrix of the position at time t, and then we have a better computation for the covariance matrix of the estimate. And then the remaining steps remains the same as classical common filtering. All right, so what we have done so far is developed a switching common filter approach to utilize the CKM to enhance our tracking. And the essential idea is try to like switch the domain, right? Try to monitor the domain, whether it is a line of sight scenario or an line of sight scenario. When it is a line of sight scenario, how do we handle the path birth and path death process? This is all to be done by the information from the CKM. And this is developed under a model-based approach. Now, next, we want to look at the methodology using deep learning, right? The benefit of deep learning is that it can be more flexible. We don't have to specify a parameterize a mobility model. We don't have to be constrained with Markovian mobility. We don't have to be constrained with AR model, first order autoregressive model for the transition of the CSI, right? It can be more general. And we hope that by like enrich the parameter of the deep learning model, the model can have a capability to adapt to more sophisticated scenarios. Now, to begin with, I would like to make a comparison between a conventional DNN design to our design. Right, a conventional DNN design refers to the design that where we don't have a tailored CKM structure, right? More specifically, let's say just we design some deep learning model. It could be a fully connected network, it could be CNN, etc. But it does not have a standalone CKM structure. It predicts the full CSI from sparse CSI observation, where it is considered to like memorize the historical CSI data or knowledge in using the parameter or the coefficient in the DNN network. Now, what makes it different from our design to the conventional design is that we try to use a standalone CKM structure, right? We call it the embedding, CKM embedding. It is essentially a dictionary where we have a bunch of high-dimensional vector, where each vector represents some CSI feature attached to a specific location. We want to use this structure because we hope to make the whole thing support a plug-and-play function, which means that after the training after successfully train the network, we can like transfer the network to a new environment without retraining the entire network, right? Where we only need to plug and play the the CKM module, right? Or I plug and play the CKM module in a new environment, and then probably I just use a very few amount of data to fine tuning some like parameter and then to make it work. So this is the overall structure. We try to construct a learnable dictionary, right, where the vector represent the covariance matrix of the series of x at position x. So we have many positions from 0 to k. By discretizing the area of interest, And then for each of the position or for each of the cell of the location, we hope to learn so-called embedding. And this embedding would represent CL of X. Now, although CL of X could be complex, but then the embedding could be represented by real numbers. And then we construct such a structure starting from sparse CSI input, and then we have a CSI structure to like extract the spatial correlation, spatial information of the CSI, and then we have a module to extract the temporal correlation of CSI, and then we try to compare the latent CSI representation with what we have stored in the radii map embedding, and then try to figure out where the location, where we are. So let me briefly talk about each of the important modules. The first one is the CSI feature extractor. So we call that the CSI contains spatial information, right? But the challenge is that can be fully random, right? This is one thing. The other thing is that we can only make a very sparse observation from the high dimensional CSI vector. So to extract the information, our design strategy is to put up a transformer with a self-attention and CNN, where the transformer will try to extract the spatial correlation from the antenna space or the angular space, right? Because the CSI would roughly tell where the user is based on the angle of arrival of the propagation path, right? So we try to use self-attention mechanism to exploit this information. Although this is difficult, right? Because our observation is very sparse. So this is why it is followed by a CNN structure where we try to correlate the adjacent observation to tackle the challenge where we have randomness of the channel and sparsity of the observation. So this is CSI feature extractor module. And then after that, we also try to exploit the temporal correlation between subsequent measurements. And this is very important because there's a hidden mobility or a hidden mobility pattern from the CSI observation. And we hope this mobility pattern can be memorized by the coefficient in the neural network. So what we are doing is that we construct a so-called bidirectional recursive neural network, where this where each line here represent an observation in time. So this is time 0, time 1, etc., up to time L. And then we have RNN to try to exploit the temporal correlation, right? But then RNN can only exploit the correlation from one dimension, from one direction, from the beginning to the end, right? We also want to exploit the direct from in the backward direction, right, from the end to the very beginning. And then for the same reason, due to sparsity, we also put up a CNN module followed by a deep CNN module, try to handle the randomness and sparsity of the observation. Then with these two modules, we have acquired a latent representation of the CSI. So the last part is try to correlate the CSI feature with the embedding vector of the radial map. And then we inject this correlation to a fully connected network. And here comes the challenge. We can predict we can come up with a bunch of candidate position for the user, but then these candidate position are scattered around in the area. So we need to use some tricks to vote for the best possible position. What we do here, which may not be the most efficient way or may not be the optimal way, we find that it works. The methodology is that we use a t-distribution, right, to reshape this data as the output from the FCM, as the estimate, to compute the distribution of the position, so that we can simply output the most likely position and the corresponding CSI embedding vector, right, as the CSI latent representation for that particular position, right? So this is how we try to extract the location information as well as the CSI representation from the sparse and unlabeled CSI data. And then the subsequent step can be quite straightforward. We can use some conventional CSI tracking algorithm, right, to reconstruct the full CSI, or here we construct a generated branch to generate the full CSI, or maybe we generate the CSI distribution, right, if we are less certain, right, if it is quite noisy. And here, the CSI latent representation that we have acquired, right, from the pipeline before, can be unstored as a geometric prompt to the generated process. Now here we can see the benefit of using a deep learning over model-based, right? Although I always think that is not a fair comparison, because for deep learning we have a large network, then we use a lot of computation. But then if we just focus on the performance, then we see some substantial difference. Now, so this is the ground truth, where the user follows some trajectory with non-uniform speed, right? For example, this part, it moves very fast, and this part, it moves slowly. And then at this point, the user also, the user make a sudden turn, right? So this kind of mobility is very difficult to describe by a conventional model, a conventional, say, Markovian model, right? So if we use model-based approach, switching Kalman filter, it can roughly recover the trajectory, but not smoothly. And at the turn point, the mobility is quite non-uniform. Now, for a learning-based approach, it recovers the trajectory quite, at least very smooth, and it successfully recovered the non-uniform velocity at this segment. Now, although there's some deviation from the true location, right? So this is due to the noise. This is due to the capability of the deep learning model. Now, we also have some method from the state of art. So this stands for the channel charting. So the last part is that we try to investigate how the CKM may provide some guidance for a CSI probing. Now, we have already explained how CKM can assist for CSI tracking, right? And then CKM can also provide some information to guide us how to optimize the sensing matrix adaptively. So existing solution is to do some hierarchical beam sweeping, or more in a much simpler way, we can simply do some random beamforming, right? So just to utilize the idea of compressed sensing, we can do random beamforming. Now, however, CKM actually provides approach as a byproduct of the tracking to give some hints of where to steer our beams to make the tracking more efficient. It turns out that as a byproduct of the switching Kalman filter, we have computed a so-called covariance of the prediction error. Right? The covariance is given by here. And then it turns out that the differential entropy of the estimate h of t is given by a formula that only depends on the covariance of the prediction error. So for those who are not quite familiar with information theory, the differential entropy simply measures how certain or how uncertain the estimate is. So what we are trying to do is that we are trying to minimize the differential entropy, right? for the best probing vector. And then this is somehow already available from the switching common filter approach, which is given by this vector. And then we can, and then we find out that the optimal solution or the optimal probing vector or the optimal sensing matrix is given by the dominant eigenvectors of the covariance matrix of the Purity error. Right? So this gives us a guidance to like steer the beamforming vector for channel probing. Now, alternatively, we can use the generative branch in deep learning method to compute the probing vector. Right? For example, we can do bandit learning because for the generated branch, it not only output generated CSI, it can also output the distribution of the CSI. Right? Once we know the distribution of CSI, we can use, for example, epsilon gradient or Thompson sampling approach to come up with a probing vector. Or we can use deep reinforcement learning for a more sophisticated objective. In particular, where when we have multiple users, when we have multiple base stations, then the probing strategy can be very complicated because the base station can share some correlation and user can share some similarity. Then we may have a more sophisticated design for the probing strategy, right, based on the statistics of the CSI. So let's see some experiment. So we do this in a simulated environment. So this is some city picked in, I guess, is San Francisco. So we have 7 base stations, and then we consider 64 antenna planar antenna array, dual polarized, and then we use ray tracing to simulate the channel, where we consider both reflection, diffraction, blockage, scattering, etc. We simulate up to 250 propagation path for each of the transmission, meaning for each of the transmitter-receiver pair. And then we also have 2 types of routes. The users can like travel along some predefined street or avenue, or it can like go everywhere, following non-smooth trajectory. And then we also consider different environment with or without the vegetation. Now, so here is the evaluation in terms of the capacity that we can achieve using the model-based approach, meaning we use the switching common filter approach. And as we mentioned, that we are interested in the extremely sparse pilot scenario. Specifically, we just send 1 pilot in every 10 milliseconds. And we consider a mobility at 36 kilometers per hour at SNR 20 dB. Now here illustrate the channel capacity in terms of the time in the tracking. Let's first pay attention to the yellow line, which illustrate the performance of the conventional common filter. Now we see that, and we also need to point out the blue curve that represent the best possible performance under perfect CSI, which means that we don't do estimation, we just know the CSI. Right. Now, in the line of sight scenario, common filter can achieve like roughly 50% of the best performance. However, it most likely achieves nothing in non-line of sight scenario, right? Because of the so-called domain switching problem for conventional common filtering. But for the proposed, referring to the switching common filtering, we can track very close to the perfect CSI case, right? We can achieve up to like 97% of the capacity. So this illustrates the capacity efficiency ratio, which is computed by the capacity achieved by each of the scheme divided by the capacity achieved by the perfect CSI. Right. So for common filtering, the efficiency is is not very good when we have the non-line of sight scenario. So this is purely for line of sight, right? So for common filtering, the efficiency is not guaranteed to be very large. It can sometimes drop to like below 70%, even for line of sight scenario. But for the switching common filter, it is very close to 99%. So this illustrates the localization error. While surprisingly, the localization error is not that good. It is at the order of 10 to 20 meters. So that means in some scenario, the localization precision is not that important in terms of CSI tracking for capacity boosting. Now, this is for pure non-line of sight scenario, right? Because if we look at the base station that is in non-line of sight for a particular trajectory, now we see that for common filtering, the capacity ratio is very low, right? Close to zero. For the proposed scheme using switching common filter, it can achieve slightly more than 50% to the full capacity of the system. Now, trajectory recovery, we also compare the trajectory recovery between the deep learning approach and LSTM. Right, for LSTM, the problem is, well, it can roughly recover the trajectory, but the problem is it does not do well for the beginning of the trajectory and the tail of the trajectory, right? Because the LSTM can only exploit correlation that focus on one direction. But in our design, our initial design has similar performance as LSTM, but then we discovered that we need to use the bidirectional RNNN to capture the correlation in both directions. Now, using this trick, we can resolve the issue of the large error at the very beginning and at the tail. So we also compare the throughput between the model-based approach and the learning-based approach under some scenario that is not favorable to the model-based approach, and then non-uniform mobility, non-Markovian mobility, etc. So we can see that using deep learning approach, we can achieve the performance very close to perfect CSI, but then using a classical model-based approach, because of the inaccuracy of the model, then the performance degrade a little bit. Okay, so finally, can we still learn the CKM in this complicated scenario where we need to simultaneously track the CSI and recover the position? Now, it turns out that we can, but we need to use some offline training, right, from a massive amount of data, right? And then we also probably need to use some position prior to guide the model, right? No matter whether it is SKM model-based approach, or whether it's a deep learning model, we need to use some rough position prior to guide the training to converge to the right position, right, to the right parameter. But the good thing is the location prior, we do not need to rely on a high precision location prior, right? It can be a very coarse. For example, this prior can come from base station position plus very coarse RSS-based localization method, or it can come from base station position plus some propagation model. So as long as we have a prior at the accuracy of like 50 or 100 meter, then with sufficient amount of data in the outdoor scenario, we can have the convergence. So this slide is a little bit complicated, but this simply gives you an idea of how it may work in a model-based approach. So where although we only have a very sparse observation of the channel, we can come up with some signal processing approach to like formulate an unbiased estimator of the coherence matrix. And then we can also show that when the number of observation goes to infinity, the error of the coherence matrix estimation in LG norm can decays like 1 over square root of t, where t is the number of observation. All right, to summarize, so we spent 1 hour to discuss the approaches for CKM utilization with data that without location labels. So this is very important because it can be quite general. And then we discuss self-localization radial mapping methodology to tackle this issue. Well, this may not be the best one, but it works in many scenarios. So the philosophy is that we first recover the location labels from a large amount of CSI data, from the CSI data, and then we utilize CKM from the location labeled data for CSI tracking and guided CSI probing. And the philosophy that makes it work include the tool to make it work include a model-based approach that we have introduced. We introduced a CKM-assisted domain switching for common filtering. And we also introduced a learning-based approach, where the essential component is to try to extract CSI latent representation via spatial temporal CSI feature extraction module. And then we will try to correlate the learnable CSI embedding. We try to correlate the CSI feature, right, with the learnable CSI embedding. And the reason that we make an architecture with a learnable CSI embedding is because that we hope to support CKM plug and play so that it can easily transfer to a new environment. So this is still very preliminary. We still find some many interesting things to explore in the future. Now, for example, what can we do for a multi-user and multi-base station scenario? So there's a correlation across user, across base station, and then we may need more efficient strategy for CSI tracking and CSI probing with the system of the CKM. So this has not been attempted in the literature. We may also need to adapt the strategy to various design objectives and challenges. For example, we just talked about maximizing the capacity. Probably we can consider minimizing the delay or maybe joint communication and sensing objective. Right, so this brings to the third point about joint radar sensing and communication. How may CKM help in this scenario? In particular, in the case where we don't have precise location labels for free. All right, so this is some reference. And with this, I would like to thank you for your attention. And yeah, I hope you enjoyed this lecture. And we welcome any questions.
Okay. Yeah, thanks, Professor Chen, for the very insightful talk on blended utilization of CKM for CSI tracking. So both the model-based and the deep learning approaches are discussed. So we have got quite a number of questions. The first question is, you mentioned that the statistical characteristics of CSI variation are highly dependent on the location xt. So what is the core physical meaning of the location-dependent covariance matrix, so which is C bracket of xt? So how is it related to the spatial characteristics of the propagation environment?
Right. So our argument is the following. So if we focus on the outdoor environment, right? So the scatters mainly come from the big buildings, or maybe the road, and these big building and road are static. It won't change for a long time. Of course, the channel is also affected by the moving scatters, right? So the component come from moving scatters is denoted by H epsilon. So this is considered to be small. This is also verified by our not quite rigorous simulation platform. But the question is closely related to our model for HFS, right? HFS, as we mentioned, comes from the channel, right, from the scatters. Now, if we look at the downlink channel, right, the downlink channel describes the H antenna as a base station towards the user, right? So the channel, right, only depends on the AOD, right, angle of departure at the base station, right? So the first hop from the base station to the static scatter played an important role for the steering vector, right? So this steering vector span the subspace of the channel, the subspace of dish X, and then this AL that characterize the amplitude and phase of the path, right? Plays like control the randomness in the subspace, right? So due to this subspace model, then we can like consider that the H of S, right, lies in the subspace that is represented by the covariance matrix theta X. And so in this example, right, when we move from xt minus 1 to xt, then the scatter may change, right? The scatter may change from this building to mainly this building, right? So what is changing is the AOD is changing, right? Previously, this AOD play a dominant role, and then when we move from xt minus 1 to xt, this AOD play a dominant role, right? This corresponds to shift of focus from the subspace spanning by this steering vector to the subspace spanning by this steering vector, right? So from this point of view, we consider that the covariance matrix or the subspace of the channel is strongly location dependent, right? In one sentence, it is because of the static scatters.
Okay, yeah, great. So the next question is, I think you briefly mentioned this in your future work. So the framework is modeled based on single user joint CSI and trajectory recovery. So can it be smoothly extended to multi-user scenarios? In multi-user scenarios, can the measurement data of multiple users be reused to jointly improve the modeling accuracy of CKM and also the performance of joint recovery?
Yeah, I think this is a very, very good question. Actually, in our experiment, we actually simulate many users. So these red points are the users that we deployed in this environment, right? And then based on these red points, we like simulate multiple trajectory, etc. So in terms of CKM construction, we actually accumulate the data from all the users to construct the CKM. So back to this question, the more user, the better CKM construction performance we can achieve. Now, the question is also related to channel tracking, right? What we are currently doing is we treat each user individually. So we are doing a single user tracking problem, and we apply this problem to each of the user. The multiple user would like give benefit for CKM construction. So if we have multiple users, we have more accurate CKM. But for the tracking performance, we currently only handle each user individually. So this question actually point out a very good future direction in the sense that when we have multiple users, we probably need to upgrade the the tracking structure to make a better use of the CKM. Right. So yeah, this is a very good direction to explore in the future.
Okay. So here is the next question. So in the Bayesian framework for joint CSI and position recovery, is there a coupling game between CSI recovery accuracy and the position recovery accuracy? So that is, will more accurate position information improve CSI tracking performance and vice versa? So is there any theoretical analysis to quantify this coupling game?
Yeah, this is a very challenging question. Yeah, indeed. The performance of the position estimation and the CSI estimation is coupled. For now, we don't have any analysis on the joint performance, the so-called coupling gain or coupling loss, because it is difficult. This is difficult because it is the problem is actually non-convex, and we solve it using alternative optimization. So the answer is that we don't know. And then we also feel that the analysis is very challenging because of the non-convex nature of the problem. Yeah.
Okay, yeah. The next question is SKF, so switching common filter, a specific implementation algorithm for the previous Bayesian joint CSI and the position recovery framework? So compared with the traditional common filter, so what are the limitations of common filtering does SKF solve by introducing the position distribution tracking?
Right. So the first question, yes, the common filtering solves this problem. So this is the answer. Let me see. Yeah, the common filtering solves this problem. So solving this problem have in general two approaches. One is using dynamic programming, where there's some standard approach to solve this problem. The second one is use common filtering, which is an iterative implementation of the dynamic programming. So the short answer is yes, the switching common filtering solve this problem. Not sure if they solve this problem optimally. I guess no, because of the possibly non-convex nature of this problem. But I guess in some sense, in some special scenarios, the switching common filtering will solve this problem optimally. For example, if the propagation scenario remains solely in line of sight scenario, then this switching common filtering can degenerate to a conventional common filtering, right? Without domain switch, the two things will be the same. In that sense, the switching common filtering may optimally solve the original problem, where the problem becomes convex. And not sure if this is the 100% accurate answer, but this is just my quick feeling for this question. The second question is how switching common filtering is related to the conventional one, and solve what it may not be doing for the conventional one. The essential difference is let me use this. The essential difference is the red part. In the conventional common filtering, we don't have any statistics of the disturbance. So we simply imagine that the disturbance is IID. So that will correspond to tracking a system where the disturbance is IID. Right? So this will be similar to tracking a system with a linear transition and an IID Gaussian disturbance. So this is conventional Kalman filtering. Now for switching Kalman filtering, we are interested in the case where the disturbance is location dependent. And in order to track this system, we only need to update the statistics estimate. Now the statistic is location dependent. So the only difference between switching Kalman filtering and the conventional Kalman filtering is this term. And to estimate this term, we only need to introduce the green part, where we need to maintain some iterative formula for the distribution of the position and the updated formula for the covariance matrix, the covariance of the arrow of the estimator, right? Which depends on the CKM, right? Which depends on the information of the covariance matrix that is location dependent, given by the CKM. Right. Hope I make this clearer.
Yeah, I think it's quite clear. Okay, so maybe we have one more question for the sake of the time. So I think this question is related to page 22 or 23, I guess. So the question is, how is the output of the CSI feature processing module connected to the previous SKF algorithm and the Bayesian joint recovery framework? What gains can it bring to position tracking and CKM modeling?
Yeah, this is a very good question. We actually try to think in this direction, try to make connection between the deep learning structure and the conventional Bayesian framework, but it is difficult. But we can like illustrate from the high level approach, right? We try to the conventional Bayesian framework is try to exploit the correlation between the observation and, let me use this, try to exploit the correlation between the observation Y and the position X, right? And then by using the correlation between the position XT, right, given the previous position, as well as the conditional probability of the observation YT given the position XT, right? So this is the Bayesian framework. And the deep learning model tried to exploit this correlation using the CSI feature extractor and temporary context encoder, in the sense that we developed this module in a way to try to extract the correlation across measurement samples, as well as correlation across antennas, right? To extract the correlation across antenna, we use a self-attention module. To extract the correlation across measurement, we use CNN as well as the INN structure. So I know that this may not be a unique way to design a deep learning model to achieve such kind of correlation extraction kind of thing. But we try many different combinations and figure out that, well, this kind of structure works the best. And then we, from our standing, the coefficient of this network simply try to memorize the mobility pattern, right? That was described by the mobility model in the Bayesian framework. where the mobility model under Bayesian framework is restricted to some parametric model, but then the mobility information is believed to be memorized in the coefficient of the deep learning network. So I'm not sure that I have answered this question, but this is the best I know from our experiment and our design.
Okay, yeah, okay, great. Yeah, due to time limitation, I don't think we can go through more questions. And once again, thanks Professor Chen for the wonderful talk, and thanks everyone for joining us today. Yeah, by the way, yeah, we have 2 more lectures for this course series, and next week we are going to talk about the data set and prototypes for CKM. Yeah, everybody, you're welcome to join us next Wednesday. Okay, again, thanks Professor Chen for the wonderful talk, and thanks everyone. Okay, bye-bye.
Thank you, everyone. Bye-bye.
Bye-bye.